we now turn to flow control, and this is in fact a couple of chapters. Again, the textbook have very concentrated short chapters, so it's a quick read. So we've been talking about topology, which is how you connect nodes together. Once you have that topology, you can decide on the route, and that's routing. You can try to balance the traffic by using adaptive routing or using randomizations. But most of that, we are thinking really about a packet in isolation. I decide how to get from one place to another, and what if there are multiple packets happening at the same time and they can conflict? So here's an example. Let's say I have this channel is all going in this direction. That's the incoming. Both of them wanted to end up here, so they both want to use that channel. If they both come at the same time, then clearly they cannot all go through the same channel at the same time, the downstream channel. Okay, so just like traffic. Okay, when you have intersection, you cannot allow both traffic to go on at the same time without some sort of coordination. And that's what traffic lights do. They stop certain traffic to allow other traffic to go through, so you don't have conflict on the same resource, the channel. But unlike in traffic light, where the road itself is also the parking space. When I stop traffic in one direction, really cars just stay on the road. Okay, that's where they stop. Now, in the network, we can't do that. We can't freeze the packet in the wire. So what happens is you need to have buffers. So then one packet can stay in that buffer to allow another packet to go through, and subsequently when the channel is free and this second the second packet can go through. So this is called flow control. There are different types of flow control. The one extreme of it is circuit switching. That's what used to happen on a telephone network. What you do is you go through all these connections and you establish a hard wired connection. You have a telephone over here, you have a telephone over there. They go through switching stations. So this is being hooked. A fixed connection is established, and then both sets can talk on this reserved piece of wire. There's a wire that's connecting from the source to the destination, and your signal just flows on it continuously. There's no packet. Okay, so that's one type, one end of the design. Most of the network today that we're dealing with, they don't have this long streams. So it's all packets, and we go with the buffered flow control. So the thing that we need to allocate here are twofold. The channels, who gets the channel, and the buffer, who gets the buffer. And you can allocate the channel and buffer at different granularity. Remember, from the user's perspective, and I don't mean persons sitting in front of a computer. The user of the network is this core plus its cache, okay, this node, compute node. It will send you information, it will send you packets. From the core's perspective, the unit is packet. I'll send you a data packet, a metadata packet. They have different lengths. But from the network's perspective, the unit that is often picked is for flow control purposes, hence the name FLIT, flow control unit. And that's more standard. Maybe it's 32-bit, maybe it's 128-bit, some number. And so therefore you have these two granularity, packet, FLIT, and you can manage both the channel or the buffer at either granularity. You can say I have some buffers, they're all based on flits, and I'll give you 1, 2, 3, a number of flits to host the packet. So it may not be able to host the entire packet. And the channel can also be allocated. Once you get it, you get the whole packet to go, or once you get it, you can only send a flit at a time. So if you look at the possibilities, there are these two sides, packet, flit, and you can allocate buffer or channel based on them, and you get these 4 different combinations. I'm managing everything on the level of packets, so that would be this node over here. I'm allocating my channel based on flit, but my buffers are based on packet. That would be this, and so on and so forth. So what is the consequence? Why we don't have this? Let's think about that for a moment. The reason we have this is primarily in the network domain, where you would have a node, and then this next node may be kilometers away from your fiber, kilometers away from your previous node connected using fiber. So if I allocated the channel for a packet, I have a packet to send. I already got the allocation, and I send the whole packet downstream. And when I get to the destination, I want to find a buffer, and I don't have enough buffer because my buffer are managed by flits, and I don't have enough. And if you find that situation, you may say, okay, then I will keep only enough flits that I have buffer for and drop the rest and then deal with it later. And this seems terribly wasteful because this is a very expensive resource, whereas some buffer, a couple of bits, are comparatively much cheaper. So you don't want to deal with that situation. Hence, we don't have this node. Okay, so if you're sending an entire packet, you better make sure that at the end of that node you have enough storage to hold the entire packet. So the only thing available for that would be both being packet. On the other hand, if your channel is allocated by flit, you can still have storage at the end for the entire packet. That may be an overkill, but that's fine. Okay, so because of that, we have these 3 different cases, and that has implication on the timing, and we will see why we even have the distinction of these. Here's the timing. So remember, maybe we should draw this this little thing that we just had before, right? So that's channel, that's buffer, and channel can be packet or flit, packet or flit for buffer. And we don't have this. This is store forward, this is cut through, and this is wormhole, right? That's from the previous slide. So if everything is handled by packet, then we send the whole thing, as this is in general in this slide. This is the direction going forward, going downstream. So you have one hop 1, and then this is what happens at hop 2. Okay, as time go by, certain things start to arrive, and so you at node 1 you start to route. After some time you decide, okay, I'm going to node 2, and you send the entire packet, which contains a header flit, a tail flit, and a whole bunch of body flits. And when everything arrives at the destination, that's when you have the packet, because the unit is packet, so you don't wait for flits. When the packet is there, you start to route, and when you have a route computed, you may not have the channel. The channel may not be ready, so you may have some idle time waiting for the channel to get ready, and once it's ready for you, you send the entire packet downstream. So this is very coarse grain, and you can see that all the serialization delay gets exposed. This is almost like I don't have a pipeline, the processor. I'm handling one instruction at a time, and this instruction can take several nanoseconds long, and that's my cycle. Couple of nanoseconds, that's my cycle. Realizing that we can borrow the concept of pipelining, cut through tries to do this thing a little bit differently. So once the header flit arrived at this is again your node 1, and then downstream neighbor node 2. So once we arrived at this, node 2 can start to do the routing already. Oh, I know where you're going to because that's what's in the header. And then I start to route. This is overlapped with the arrival of other flits in the packet. And that's perfectly fine. And I can then start to send the packet even though other flits are still arriving, which is fine. They're overlapped. They're not dependent. I already have H. H is there. So I do have it. The dependence is met. I don't need to wait for T. T is being sent then. So this is all perfectly logical. Now imagine there is another node. That node starts to a third node, right? Which is here. That node got the header, but for some reason couldn't send the packet. Let's say there is a 1 cycle bubble because the channel is not free. Well, this is perfectly fine because we got node 2 got the capacity of, remember, this is here, cut through. The buffer is allocated by the packet. So when the packet arrives, the entire packet can stay at node 2. There's sufficient buffer. So even though a downstream neighbor cannot buffer your early thing, your entire packet yet, node 2 is already sending to node 3. Node 3 can have this from going forward, going to its downstream neighbor. I can't do it now. I will have a delay, and later on I will send it, but this doesn't impact node 2. Finally, in wormhole, I am reserving enough flits for my packet. In other words, when one gets the go ahead, it will send the entire packet. This is coming, but I know that I am also in parallel starting to send out, right? This is the same thing as with cut through early on. So I know that in normal cases, when my tail arrives, in this example, when my tail arrives, my header flit 1 and 2 are already gone. So really what I needed to keep is perhaps these 4 flits, okay? So this is, in my example, the routing takes the amount of time for 3 flits to arrive. If the routing takes 1 flit, takes the time for 1 flit to arrive, then I know at most, not at most, but in the typical case, I only need to buffer 2 flits because the downstream node would be sending H here, B there. So by the time H is sent, I don't need its buffer. I can reuse that to store the next one, okay? Or maybe you have one more, just if you worry about the turnaround issue, whether I can give you the buffer in this cycle. But that's the point. The point is I know that they are also being forwarded to the next downstream node, and therefore the downstream can quickly get rid of the need for the buffer, and therefore I don't allocate buffer for the entire message. But then what if, in this case, at node 3, I got the header, all right. Let me perhaps clean this up a little bit. So at node 3, I got the header arrives, and I start to do routing. And at the end of the routing, I know where I want to go, but I can't send it at the moment. I can't allocate the channel. It's busy. It's serving another packet. Therefore, I have to keep buffering the incoming flits. But at some point, that buffer is running out. I don't have enough buffer, and this would have to be back propagated. So the subsequent transmission of B and T is being delayed. So the channel right here, if you think about the channel, this is really showing, this line over here is showing the channel between 2 and its downstream neighbor, right? I sent 4, that took all the buffer from node 3, and I run out of buffer, and therefore I have to stop. And this becomes empty. And this is sort of why I guess it's called wormhole, that this is, the packet is like a worm. It's kind of crawling through these nodes, and its head, it's at one point, this is what's happening. These 4 flits actually are arriving already at this time. They have already arrived at node 3, sitting in that buffer, but the other 2, the tail of this worm, is still sitting in the buffer of node 2. Okay, so there's these general categories of flow control. Again, because storage is comparatively cheap, at least in general networks, we usually deal with cut-through, because we don't want to have to deal with situations like that unless your packet is really long. For instance, it's unlimited. You can have a packet size that is not limited by an upper bound. Then you can never reserve enough storage, and you might want to have a wormhole routing. So here, the downstream congestion forces the upstream channel to idle, and we don't like that. Okay? The channel being idle is usually a bad thing, because there tend to be the expensive resource, especially in a large-scale, wide-area network. So how do you solve the problems like that? You will see this concept used again and again in interconnect. It's called virtual channel. There's a saying in computer engineering / computer science, if there's a problem, add another level of indirection. This solves all your problem in virtual address translation, what have you. So virtual channel is kind of applying the same tool to a different problem. I have a resource. Logically, this is over here. Logically, I need to stop the channel because I don't have storage downstream, so I have to stall and making the channel idle. But if that's a logical channel and I have more than one of them, and I can multiplex the same underlying resource. The physical channel is sometimes serving virtual channel 1, sometimes serving virtual channel 2, then the physical resource is not being idled. Okay, so if we're not tying the state of the packet to the physical channel, we're tying it only to the virtual channel, and we solve the problem. And you will see that we use virtual channel. It's basically the same thing that we use to solve a whole bunch of different little problems in interconnect. So this is what we discussed, is basically how we like the system to work, right? Going back to this idea. We want the channel to stop sending because we don't have space over here. This idea here, that once we exhausted this, we want the channel to stop pumping the same packet to me because I cannot keep it. But how is this actually done? And that's usually done through a credit system. But it's, in general, it's a buffer management issue. You can have different buffer management, but credit base is perhaps the first one that we discuss when we talk about these. And the idea is, you have to, when you run out of buffer, you have to back pressure. You have to tell the upstream not to send you, and that will potentially back pressure to even more upstream nodes. So how do you exert this back pressure? Okay, you have credit. You give your upstream neighbor the number of buffer entries available on your node. Okay, if you can take 50 flits from the upstream neighbor, you give him the number 50, and that neighbor would send up to 50 units to you, and it's usually managed at flit level, so maybe that's 50 flits. And when the credit runs out, that node, the logic would dictate that it will not send you more packet. Okay, so of course, if you have, so this is downstream neighbor, downstream, this is upstream. So I am going to send you packets, and let's say you have 4. So I will send you 1, 2, 3, 4, and you have 1, 2, 3, 4 buffered. And I used up my credit. My credit goes from 4 down to 0, and I will not send you anymore. But now this packet is forwarded further downstream. Now I freed up one of these buffers. Then I need to send you an extra credit, so your credit goes from 0 back to 1. Then you will send me another packet. Okay? So this is one way of doing it. We'll see some implication of this in the next slide. Another way is not to do this counting explicitly, but rather I give you a red light or a green light. Okay? When I shine red light, stop sending. When I shine green light, you can send. So this could be just a wire. Okay? I assert 1, you can send. I assert 0, you stop sending. It's more like an on-off switch. So these are sort of front end. I make sure when you send me something, I actually have the buffer for you. If I don't, I would tell you to stop before I even run out. So you will never send me more than I can handle. Another way would be to actually disregard this altogether and explicitly acknowledge every packet. So if you send me something, I don't have space, too bad, I drop it because I have no choice, and I knack you. I send you a negative acknowledgement, and you can resend. And this becomes a little bit more bothersome because your upstream neighbor cannot just let go the packet. It needs to hang on to it until it's specifically acknowledged before you can reuse the packet. So that's not a very frequent choice of design. So let's think about this notion of credit. Okay, so right now, node 1 in this picture is the upstream neighbor sending to node 2. Okay, as time flies by, what happens? Okay, as time goes down in the picture, when node 2 send a flit away to its downstream neighbor, now I get a free flit because I'm using credit system. So I clearly had the credit for node 2, had the credit for its downstream neighbor, so it can safely send a flit, therefore creating an empty, which is a credit for its upstream neighbor, node 1. So I'm sending that credit back, and this takes some time. Okay, it takes propagation delay. You know, they're not at the same location. So by the time the credit reaches node 1, I need some processing time. Granted, the processing time could be very, very short. Not even a full cycle. But there is a delay nonetheless. You have to add them up. By this time, I will, node 1 at this point, at this juncture, will know that it can send another flit, which it will, let's say in the busy case, it will send another flit which arrives to node 2. Okay, and node 2 will take some time to process this, to realize, okay, now my credit has gone down to 0. So this whole chain event is the full round trip of credit processing. Okay, it's happening. To increment your counter, decrement your counter, all of this is something you need to do, and there is the delay. Now, of course, you don't want to have just one credit, because if you have one credit, this is what's going to happen. If you have just one buffer, therefore one credit, for this much time, this whole amount of time, you can only send one flit. Okay, and the other time you're busy. What you want to do to keep the channel busy, you want the flip to be pipeline. You want to send one here, send one there. So you want to be able to send continuously. So you need to prepare for enough buffer, at least, to keep this time busy. So in other words, if your bandwidth is, let's say the credit processing time is 10 cycles, and you can send one flit per cycle, then you want the downstream to have at least 10 flits of buffer. At least 10 flits. So when the first flit arrives, you are already starting to process all this. It will keep the system busy. So the downstream, the upstream neighbor has enough credit to keep on sending, and by the time you exhausted all of this, the flit will arrive. The credit will arrive to allow you to keep on doing this. So how do you send the credit? Well, you can use dedicated wires. You can actually send a packet backward, but that obviously takes it takes bandwidth away from useful payload. You can also pig it back on other packets. So there are a number of different ways. We're not going to make a distinction here. On-off control is really similar, except you're not explicitly telling how many. Okay, so instead of telling you I have 4, so you can keep your own counter and decide when to stop, I'm explicitly telling you when to stop. And again, there is a time issue. Okay, by the time I tell you to stop, this signal may take a finite amount of time to get there, get to the upstream. And to make sure you don't lose any, you want to have enough buffers to absorb the incoming traffic during that time. Okay, so when let's say this is my buffer, I am currently half full, and I have a threshold for T off, for sending this off. Once I turn the signal on, it's not going to instantly stop the traffic. So I need to guarantee that the time the turn off is taking into effect times the bandwidth, I have that amount of buffer. Okay, so my off threshold is that away from full. And then when I drain this to a certain place, let's say that's on, at that point I need to turn it on, right? And meanwhile, I may still be sending these packets to my downstream neighbor. In other words, I'm still, even though I told you to turn on, you haven't seen, my upstream neighbor hasn't seen my signal yet. So nothing is filling this buffer. Meanwhile, I can be draining this buffer at bandwidth speed. Okay, so you want your total to be at least this big. So in the busiest time, the traffic is not stopped because of the control for either on-off signal or credit. So that's the whole idea. Now let's turn to a big topic, and that's deadlock. So we already encountered deadlock early on in the protocol discussion. This is the example that we drew back then, and assuming network is completely deadlock free, don't worry about it. You send a packet, the packet will be delivered if your receiver didn't have a problem. And then we had a problem. If we don't have enough incoming buffer, then there's so many packets, so many requests that we get from the network, and we're trying to send a reply, but our reply cannot go through because they are backed up by the other end when the other node is having the same problem of not able to sync in from the network more requests because its replies are being backed up. So this gives you the cycle or the dependence circle. And in network, you can have the same problem. Anytime you form a resource dependence cycle, like one shown over here, I have buffer 1. Buffer 1 is waiting for buffer 2, it's waiting for buffer 3, which in turn waits for buffer 0, which completes the cycle, waits for buffer 1. In reality, of course, a buffer never waits for another buffer. It's more complicated because what happens is buffer 3 is currently holding packet 3. Okay? So buffer 3 is waiting for packet 3 to depart, but packet 3 is waiting for another buffer in the system, which is buffer 0, which currently holds packet P0. Okay? So this gives you the dependence, the cycle. How does this happen? Let's give you a more realistic example. Here, I'm not drawing everything. I'm drawing 4 nodes and the incoming buffer. Okay, this is only the incoming buffer. What that means is, if I have a packet that I need to send from, let's say, this node over here to that node, there's a wire, or there's a channel, lots of wires, and the packet will eventually arrive. When they arrive, the first thing they do is they get written into this buffer. So there's a buffer dedicated for the incoming channel from your west neighbor, upstream neighbor, from your north upstream neighbor, from your east upstream neighbor, and so on. And remember, every node in this direct network is also attached to a compute, to a client. This is your core with its directory controller, with your cache controller, everything. Okay, and it can decide to inject a new packet into the network, new packet completely formed. So that would go into the local channel. So here's the situation for a real, it's not just, and for simplicity, all of these buffers are 1 deep, only 1 packet. Again, in real world, you have probably many more than just 1, but this is serving for the example. So now let's say I have these 4 compute nodes, clients, each generating 1 packet simultaneously in the same cycle. Boom, they all come in. And they all want to go to their counterclockwise neighbor. So packet 4 over here wants to go there. Okay? What will happen? If that's all we want, we're done. You see? Going back a little bit. If we all just want to make 1 move, excuse me, then it's fine, because after arriving at this buffer, they can go out of the ejection port, and we're completely fine. But imagine, rather than this, if we go back 1 step, 4 wants to go 2 step to the counterclockwise neighbor, meaning 4 wants to get there. 3 wants to get here. 2 wants to get there. And 1 wants to go there. Okay, is that messy enough? So let me clean this up. Suppose that's the case. And now let's follow the cartoon what happens. Okay, first cycle, they get generated and get stored exactly at the same cycle. They want to go. Because this is going following this channel, it will arrive at the south incoming buffer. And all 4 buffers, all 4 packets will get their corresponding, sorry, wrong direction. And now they all want to make their left turn. or counterclockwise turn. So now 4 wants to go to this node, right? How many buffers are there? 0. So it cannot move. It's waiting for 3. Simultaneously, 3 is waiting for 2, 2 is waiting for 1, 1 is waiting for 4, and we get ourselves a deadlock. How do you solve the problem? Okay, what gets you into the problem? A complete cycle. You have to break it. How do you break it? Lots of different ideas. What if you, instead of having this all in a planar location, you kind of have, I don't know if I can draw this, something like that. Okay, it's a helix going up. So if I make a resource dependence, I'm doing this, but it's not closing, right? Yeah. So if I am here, so if I have 4 nodes and I want to go left, I will go, let me try this slightly differently. So I'm gonna draw this more of a 3D. Okay, I have these 4 nodes. Each has its own buffer, but more than one. Okay, and so there's another one. There's another one on top of this. There's another one on top of this. There's another one on top of that. Okay. So ground floor, next floor, ground floor, next floor, ground floor, next floor. So if I'm here, I want to turn, I'm going to depend on the resource there. Now I didn't draw enough. Here's your 3rd floor. If I want to make another turn, I have to wait on that one. If I want to make another turn, I will wait for that one. You see what I mean? But by going in this way, then I am not completing a planar circle. It's a circle that changes the height. So if I'm here, I want to go to the next node, I will always get its 2nd floor. This is node 2, so 0th floor to 1st floor, B1, 2, and then here to 2nd floor, B2, 3 on node 3, and finally here, node 0, B3, 0. You see, I have no cycle. Okay, this is open-ended. You can keep following anything, they will never return to the same node. Now, this obviously would require you to have a very tall tower, because every step you make on the network, you're going 1 story above. If you travel 25 steps, you need at least 25 stories of buildings for you to be able to do that. So you don't have to change floor so quickly. You can apply the idea of international date line. So you can arbitrarily decide it's there. So as you go 270 degree, you're not changing. Sorry, maybe this. But the last 90 degree of turn, this is when you need to go. So anybody who is moving to east, south, west, you don't have to request for any increase in the story number, but when you're going north, you do, and that guarantees you don't have a cycle. Now, if you have all these buffers lying around, maybe some of them will never get used because they mismatch in the height. So the classic idea is to overlap the resource. So I may have these buffers dedicated for class 0 or height 0, these dedicated for height 1. So I may be going to a node where I don't have any class 1 resource, but I have lots of class 0 resource. Sorry, I cannot use them because there is the potential, the small probability of having a deadlock. I cannot use them. What do you do? Here's one optimization over there where I have shared resources. Class 0 and 1 have shared resources from B1 to B30. This is, anybody can use. Okay. But B31 is dedicated for class 1. B0 is dedicated for 0. Okay. So some resource is dedicated. Okay. And that therefore the property that we already discussed over here, that I don't have deadlock, is still valid. Okay. Another idea of breaking the cycle is to not allow certain type of turning. Remember, if we all want to turn left, in my very early example, if we all want to turn left, then I have this problem. Okay, if I don't all turn left, I will not be able to form a cycle. If I'm only going straight, everybody's just going straight. How do you form a cycle or circle? You can't wrap around. Okay, so of course you have a torus, you have that problem. We'll get to that, but in a mesh network, at least, I don't have wraparound links. Going straight, I will never have deadlock. So what if I don't allow certain type of turning? So you see, you can have these turns, 4 different turns in a counterclockwise direction. You were going west, and then you want to make a left turn to go north, and so on. You have 4 possibilities in the counterclockwise turning, and you have 4 possibilities in the clockwise cycle. And if you disable one type of turn in each cycle, then nothing can form a circle anymore. Let's take an example and see what that means. Let's say in the counterclockwise, we disable this. That means, please, when you're going north, if you're already going north, you can never make a left turn to go west. Okay? That's the counterclockwise. See the missing part over here? That's what we do. Okay. So that can be married to either one of these, which cuts one circle, one step from the clockwise turning. Okay, so this is called west first. Why? Let's think about that. Here I am saying if you're going north, you cannot turn west. North to west turn, can't do that. Here, what do I say? If you're going south, you cannot turn west. South to west turn is not allowed. Okay, what if I want to go west? I cannot turn if I'm already moving north or if I'm already moving south. So what do? That means if you're already doing north and south direction, you cannot go west anymore. It's disallowed. So if you want to go west, you go west first. Okay, so that's actually an idea. The forbidding turn, you're not remembering what to forbid. It's being embodied as the algorithm that says, where do you want to go? If you want to go any node to your west, that would be the first thing you do. So you go west to the right column, and then you can do whatever you want. If you're going purely to north, south, or to east, you can do whatever you want. It doesn't matter. Okay, let's take another example. Let's say, well, let's go through all of them. Let's say I'm pairing again this one over here. Okay, I'm always pairing this one. Now I'm pairing this. I'm disallowing the north to east turn. Remember, this is disallowing this. This over here is disallowing north to west turn. Okay, once you go north, you cannot turn west, you cannot turn east. What does that mean? That means if you need to go east, west in any of these horizontal direction, you can, but you cannot do that after you go north. So if you have to go anywhere to the north, first do your east-west routing. Once you got to the right column, you can go north. So north is your last thing to do. But if you're going in the south direction, doesn't matter. Okay. Okay, I'll skip this one. You can play on it. It's really the same idea. The final one is an interesting thing. You can't do that because that's going to create trouble for you. And let's see why. Again, this one says if you're in north, you cannot turn west. Okay, not allowed to turn west. And this says if you are going west, you cannot turn north. So once you're in west, you cannot turn west. You cannot turn north. And if I want to go somewhere to my northwest, I'm dead. Okay? Assuming I don't double back. Because I can neither turn once I'm going north or once I go west. Either way, I won't get to my northwest direction. So this is not allowed. We cannot allow this to pair with that. So we get these three options. Okay? And you can imagine if you pick any other node, you say, I disallow this, then you can try and you can come up with all different combinations. And this is obviously only for a two-dimensional network. If you have three-dimensional network, then you have to worry about not just the planar version, what about the third dimension? Okay, if you have third dimension, then you have cycles and you have to disable all of those. So but it works very well for a lot of these existing two-dimensional mesh networks. Okay, so that's one idea. Technique number two. By the way, a very common notion is dimension order routing. Okay, which is first go on X dimension, then go on Y dimension. That's proven to be deadlock free. Why is that? This is because you're doing dimension order. Your X going dimension packet, your X dimension going packet, they can wait for any packet, okay? But your Y going dimension, it won't turn. You get it? Because it's dimension order. You go X to the column you want, then you go on that column. So if you're already going on the Y dimension, you're not waiting for anybody who's going on the X dimension. Okay? You're only waiting for other Y dimension network packets, and they eventually will get to their destination. I'm here, I'm going there. If packets are being taken out from the network, eventually I will move in that direction. Okay, that's the nice thing. Again, assuming we don't have, where is it? Fetch deadlock. Fetch deadlock is a different story, right? It's involving the node themselves not taking packet off the network. Then we have so if your system implemented mechanism to prevent fetch deadlock, then dimension order routing will not get you a deadlock. So these are preventions. Just one last thing. If you look at this picture, you say, okay, there are all these links, right? This node is going to that node, this node. There are links that allow these traffic. And if you look at the red, thing, they're still forming a cycle, aren't they? 8, 16, 1, and 21. Why don't I have, even though I'm disallowing turning, why don't I have my deadlock? Why is it problem solved? I can still see this complete cycle, isn't it? Well, pause the video, think about it. What do you think? The answer to that is it's what we're not drawing is what connects them. Okay, so the packet would come in. So inside this circle, they have different buffers, incoming buffers from the 4 different nodes, and the outgoing channels that's being drawn over here. Okay, so this incoming channel comes in it can go into it goes into a particular channel, but this channel's packet can go out here, here, or here. Okay, so there is still inside this dot, and this dot is not connected. There are many different possible connections inside the node. So if we disallow certain turn, that's what allowed this cycle to be broken. For instance, if we disallow the left to this turn, then this is broken. Even though here you can have the dependency, but this one is not allowed to happen, or maybe better shown as that's not allowed to happen, so I don't have the circle. So these are techniques to prevent cycles from forming to begin with. Okay. Another general approach is to allow cycles or circles to form and deal with it later. This is deadlock's two different type of solutions. Never to allow it and dealing with it when it happens. The general approach for this type of dealing it when it happens is to have some escape route. Okay, this escape route is 1 second. My pencil is not working. Oops, why is that? This is surprising. Okay, anyway, the general approach is to provide escape routes, that when you see something happens, you think you're getting into trouble, allow packets to use the escape route. Now, of course, the escape route has to be guaranteed to be deadlock free, otherwise, what's the point? So then what does this give you? It allows you to not forbid cycles in your regular route. Your regular route, let's just try to maximize performance or whatever you want to optimize and not worry about having deadlocks. Okay, so this is what you do. You provide two different classes of VC. You have one class called adaptive. What's adaptive? If you remember, I will choose my route based on congestion. So if I decide to turn left, I'll turn left. I don't want to be limited by, oh, you can't turn left because you've been coming from the west. You can't turn left because you've traveled from the south going direction. So you have a normal VC where you can do whatever you want, no restriction. And you have your escape VC. This escape VC is not designed for performance. It's just there to get you out of the trouble, to get you out of possible deadlock situation. Let's say you use dimensional order routing. We know it's bad under a certain traffic pattern. We know it's really bad. Okay, if you remember a slide a couple of videos ago, in a very special type of adversarial traffic pattern, dimensional order routing is horrible in performance. But that's not the point. We're not using that virtual channel to get performance. We're using it in case we run into some deadlock. Okay, so if your packet has been blocked for a long time, you need some sort of watchdog to tell you, okay, I have a timer, packet has been sitting there for 25 cycles, what's happening? Maybe I have a deadlock. Okay, then you can pick that packet and choose the escape route to say, well, okay, let's go to the escape route. Sort of you're lying in, you're sitting in highway regular lane for a long time. Now what you do? You go on to the shoulder to leave. Okay, but the point is that the analogy breaks down right there. When people drive on the shoulder to get away, they want to get away fast. Okay, but the escape route in the network is not going to get you to the destination fast. It's only faster than the deadlock, which will get you there never, right? That's the difference. So, and the escape route has to be guaranteed to be deadlock free. So let me ask you a question. Pause the video to think about the answer. If you are already on an escape channel, you're already on the shoulder, can you come back to the normal channel? Is it okay? Or is it going to bring the deadlock situation into play? Pause the video, think about it. The answer is just like, I think this is where the analogy really works very well. And the answer depends. If you are on the shoulder and you're coming back to regular lane, if you can just take your entire car and go back to the regular lane, nobody will see you on the shoulder, and it works perfectly fine. But if you try to steer in, leaves the butt of your vehicle still on the shoulder, and the head of your vehicle somehow is already in the regular lane, and then anybody like the emergency vehicle who's behind you cannot get through because you're in the way, and you cannot move because your head is already in the regular lane, which might be in a deadlock, then you have trouble. Okay, so let's say this is a very contrived example to show this, right? Suppose I have a flit buffered system, which means I may not have enough per node to hold the entire packet, okay? And so you can see I have only one packet, one flit, one flit buffer per node. The black one is the regular VC, the regular virtual channel that allows any turn. The blue one is an escape channel, and it disallows the turn that is missing here, right? If you follow this order, this is not allowed. Okay, so if you're in a blue buffer, you cannot, and you're coming from here, you cannot go into that flit. But let's say everybody is in the escape. All the numbered packets are in the escape channel. I don't know why there is a misalignment. So if you can see, maybe we can zoom this in a little bit. Okay, 2 is here, 3 is here, and 1 is straddling in 2 channels. Its head is already in the black regular channel over here, and its tail is here. And because it's doing a left turn, this is because it's no longer using the escape channel, so it's allowed to make a turn. If you have just one flit, and that would be fine, you're gone, this tail of yours is not there, then 3 can continue, 2 can continue, we don't have a deadlock. But if you straddle the 2 system, your tail is over here, your head is over there, and the black system is deadlocked because of the 3 axes over there. They all each want to turn, and we have a deadlock. Then 1 will never go, the tail will never release, and then you created a deadlock. So the answer is just like the traffic analysis. You can in this very specific situation. So that's about it. Next time we will discuss how all of this is actually carried out in hardware. This is again just part of the policy. Again, we have the topology linking all the nodes, and then routing decide how do we traverse these nodes for each individual packet. Here we're discussing what can happen when you have multiple packets all trying to do different things. First, you need to allocate these resources to make sure they don't have conflict. That involves having buffers as well as channels being allocated, and you have these 3 different approaches. And then we realize that to maintain the buffer control, you need something to denote whether you have enough buffer or not, and this can be a credit-based system or a non-off based system. Okay? In either case, once we have this buffer and we're waiting for a certain buffer, we absolutely can have deadlock, and you have different ways of solving the deadlock. Avoiding them altogether, two different approaches often used, or allowing the circle but have an escape route, and having the escape route giving you the property that is deadlock free by design, again kind of using the avoidance technique that we talked about. So that's really a major problem or a major issue in the design of interconnect: the buffers, control, and allocation. Next time we'll talk about the router design.